Welcome everyone to today's webinar, Applications of Integral Calculus, brought to you by Texas Instruments Australia. My name is Frank Moyer, and today we'll be focusing on looking at the applications of integral calculus stated in the VCAA study design, which include calculation of area under a curve, areas between curves, distance travelled in a straight line, and average value of a function. And just a reminder that there are some additional resources to accompany the webinar. There is the sheet of webinar questions, which if you haven't downloaded, you'll be able to download at the end of the webinar. After the webinar, you'll also receive a link to a revision sheet with work solutions with exam-style questions, the TI-Nspire file, which I've used in the presentation, and the webinar can be viewed on demand in the TI YouTube channel. Okay, so we'll start off by looking at definite integrals and signed areas. So we're going to start off with this cubic function, and I'm going to evaluate some integrals, and what I'm particularly interested in is the graphical interpretation of these integrals. So it's the integral from 0 to 2, 0 to 4, and 0 to 9.2. So I've started off, to save time, I've already defined the function in a calculator page. Now, I've used the assign, so that's the dot dot equals. That does exactly the same job as having define f of x equals. And the assign button is control and the template button. Okay, so first of all, I'm going to evaluate from 0 to 2, and I get an answer of 4. Now, if I wanted to do this graphically, I could do that graphically as well on TI-Nspire. Now, once again, to save time, I've already graphed and adjusted the window. Now, if you go to the menu in Graphs, under 6, Analyze Graph, number 7 is integral. There are 2 related to integrals. There's 7 integral and 8 bound area, and we'll see the difference between the two in a minute. So the lower bound, now you can either click a spot or you can just type in a number. So if I want to start from 0, I can just hit the 0 button and the 0 appears in a text box, press enter, and it locks it in. And the other one that I want, you can see as you slide across, the point across, you can see the area increasing till you get to the intersection point, and the area is 4. So you can either go to intersection point or you can just press 4, enter. Except I didn't want 4, I only wanted 2. Never mind. Okay, so I just wanted 2 at that stage. And I see that the area is 4. All right, so this is what I prepared earlier, which is the same thing, except you can actually see the coordinates of the points A and B. Right, the integral from 0 to 4, if we do it algebraically, we get an answer of 0, which is rather curious. So what's going on? So let's go back. We see that we had an area of 4, and then the area below the axis is negative. So we actually see that the signed area is actually decreasing. So it's the positive area plus the negative area. So that by the time I get to 4, it's 0. Now, it shows this strange notation. When you see that strange notation with an E and a negative, just take that as 0. Okay, and if I want the integral to 9.2, I get that answer there. If I want an approximate, I can do Control Enter, and it's about 1.7. All right, so I can do that graphically. If I go back to the graph here, okay, and I can get the value either numerically or algebraically. Now, in the graphs page, you can only get a numerical approximation. So that's the idea of signed areas. Now, sometimes I want the total area under the curve. So I'm going to do the same thing, except this time I'm interested in the total area enclosed between the graph and the x-axis over those intervals. So for the first one, it's exactly the same. So the area was just 4 because that was a positive area. That was no problem, no drama there. But if I want the total area from 0 to 4, I need to break it up into two pieces. From 0 to 2, which is positive, and from 2 to 4 was negative, so I need to subtract that integral. And I get 8. Now, if I want to do this in the calculator application, integral's not going to help me because that gives me the signed area, but I can use bound area. So what I can do is I can open up here. I can graph f2 of x equals 0, which is just the x-axis. And then I can find the bound area between the graph and the x-axis. So it's menu and analyze graph 6. And this time, instead of going 7 integral, I go 8 bound area. And the lower bound, I can either go to the intersection point or I can just put in a number, 0. And I can see this time, you can see the area, it goes to 4. And then instead of the area decreasing, because it's not a signed area, it's now the total bound area, you see that that area keeps increasing. Okay, so there it's around about 5.96, and I can go to the intersection point, I see that it's 8. So I can just type in 8, enter, except that's not what I wanted, because I only wanted 4. So, okay. So, in this case, okay, I'll do it again. This time I've created the same thing, except this time I can control A and B a bit more easily. So I can see that at x equals 4, the area is 8. And I keep going and the area keeps increasing. So in order to get the total area, you can use bound area once you have f2 of x equals 0 as your x-axis. All right. So if I want to work out the total area all the way up to x equals 9 over 2, I have to, if I'm doing this algebraically, I have to do it in 3 parts. 0 to 2, which is positive, take away the negative area from 2 to 4, and then add the positive area from 4 to 9.2, and I get that answer there as an exact answer, or I can control enter, and get an approximate answer of 9.26, 9.27 roughly, which should be similar to what I get if I just change that to 4.5 here. I should get that answer graphically as well, 9.27, which accords with the algebraic, the answer that I got in the calculator application. Okay. Now, often you get exam questions where you want to find the value of a terminal given a signed or bound area. So this time, I want to know all possible values of p so that the integral from 0 to p of that function equals 3. So, and I want to interpret the values graphically. So I've defined, this time I need to solve, I've already defined the function, I need to solve the integral from 0 to p equals to 3, and I get 4 values, although one of them is a negative value, and the function is only defined for x greater than 0, so there's only 3 that are actually within the domain. If I do Control-Enter, I get rational approximations, and I can see that it's 1.27, 2.73, and so on. So why is it that I get various values? Well, let's have a look here. So in the graphs application, I see that when I have a value of 1.27, I have an area of 3. Let's see when else I get an area, a signed area of 3, in other words, an integral of 3. So I keep going, it's 3 round about here. So round about there somewhere. So round about the 2.72, I have 3 again, and I'm getting a positive net positive integral again, and the area is 3 round about there again. So you can see graphically why there are 3 integrals. And I think that when doing integration and signed areas, it's very important to always get a graph to actually see what's going on, understand what it is that's happening. Okay, so let's move on from signed areas to areas between curves. So this is question 4 on the revision sheet, if you downloaded that. So I have 2 functions, and what I want to find is the region bounded between those 2 functions. So the first thing I did was define the 2 functions, because I'm going to need those, and I graphed them. When I graphed them, since I'd already defined them, I was able to just call f1 of x f of x and the other one g of x. And in this case, it's very easy to see where they intersect. I could algebraically solve f of x equals g of x and find where they intersect, although this is one you can do in your head. It's obviously going to be at -1 and 2. So I can find the area graphically in the graphs application, which is gives me a numerical solution. So if I go Menu and Analyze Graph, once again it's bounded area because it's between 2 graphs. So that's 8. And I want to go from the intersection point there to intersection point there, and 4.5 or 9/2. And I could do the same thing in the calculator application, just the integral of f of x minus g of x. Now from the graph I knew that f of x was above g of x, so that's why I put the f of x first, and 9/2, the same result as I got in the other application. Right, so in this next question, this is the sort of question that you could get in the extended response. So I have these 2 functions, and the area bounded by the graphs of f and g and the line x equals 4 is divided into 2 equal portions by the line x equals c. So determine the value of c. So the first thing to do after defining the 2 functions, always get a graph to see what it looks like. So that's what the graphs look like. I've adjusted the window. Okay, so let's first of all find the bounded area in this application. So Menu, Analyze Graph, Bounded Area. I want to go from this graph Okay, they're the two graphs from this point to there, and it's 20.25 is the area, I guess. Okay, now let's go back and do the same thing in the calculator application. This time, though, note that g of x is above the f of x, so I'm going to have them the other way around. Okay, so I get 81 on 4, which is the same answer. It's 20 1/4, the same answer that I got in the graphs application. Okay, so now what I need is to find C so that the area is only half of that, so that the area is only 81 on 8. So I solve the area in between from 1 to C equal to half the total area, and of course the restriction that C is greater than 1, and I get round about 3.22. So let's have a look at that graphically. So what I need, this is my line x equals C here in green, so I need that area to be about 10 1/8. So round about there somewhere. So round about the 3.22, 3.33. Okay, so using the graphs application, you can get a good interpretation of what's happening, relate the algebra and the calculus with what's happening graphically. All right, now the other application I want to have a look at is distance travelled in a straight line. So this is a very practical application which illustrates the fundamental theorem of calculus using an example which students should be able to relate to. So we're going to have a look at a very simple case to start with. So we're going to have a look at motion in a straight line at a constant speed of 16 metres per second. So the speed we're calling v, so v of t is 16. It's always 16. We're going to graph v against t, and we're also going to graph the distance travelled against time. So I've got my graph here. My graph equals 16, and over here I can see the area. So after 1 second, the area is 16, which is also the distance that I would have travelled in 1 second. After 10 seconds, 160 is the area under the graph, which is also the distance. So that clearly shows the relationship between the distance travelled and the area under the graph. So this time I'm going to plot the area under the graph against time. So I'll start the movement there. So in the top graph, I've got the area against the time, and here I'm graphing the area against time as a plot. So I keep going, and I see that I get a straight line, and I wonder what the equation of that line might be. Well, it might be 16t, or in this case, because I'm using the graphs application, I'm going to have to call it 16x, since I have to use x as the variable. And I see that, indeed, it does match all of those. So I think that's a very simple illustration of the area under the speed-time graph, giving you the distance travelled in a straight line. And it's also a very easy to understand illustration of the fundamental theorem of calculus, because 16t would be is an antiderivative of 16. So we can see the relationship between the antiderivative and the integral as well. Okay, so that just illustrates what I was saying, that the distance is given by the area under the graph. Okay, so the next question, this time the speed is given by that function. I want the total distance travelled in 18 seconds, the time taken to travel the first 100 metres, and the time taken to travel the last 100 metres. Okay, so first of all, to find the distance in the first 18 seconds, I start by defining the function. I then need to find the integral from 0 to 18, and it's around about 562 metres. So graphically, I can see that as I move along, I get more and more area under the graph, which corresponds to the distance travelled. So by the time I get to 18, (562), the same answer that I got earlier. So time to travel the first 100 metres, so I need to go from 0 to some value t1 equals 100, solve that for t1, and it's roughly 5.5 seconds. All right, so graphically, I need the area to be 100, so I just keep moving that till I'm at 100, which is around there somewhere, so roughly 5.5. Okay. The last 100 metres, so I need to solve the integral from some value t2 to 18 to equal 100, and this time it's about 15.5 seconds. So the time taken is the difference between 18 and t2. Right, so about 2.5 seconds. And if I graphically, I need that last area there to be 100, around about there somewhere, and I can see it's about 15.5 seconds is the coordinates. Okay, so once again, the relationship between distance travelled in a straight line and the integral. Okay, so the last application is average value of a function, and the formula is very easy to use, so I'm going to concentrate instead on understanding the concept of average value. So I'll start off with a pretty obvious example. So this time I've got this hybrid function, which is a linear increasing function and followed by decreasing function. The minimum value is 1, the maximum value is 8. So the average, because it's increasing and then decreasing at a constant rate, the average is going to be halfway between 1 and 8. Difference between 1 and 8 is 7. It's going to be 3.5 either side of 1 and 8. So 1 plus 3.5 is 4.5. So I expect 4.5. So somewhere near there should be the average value. Now, that doesn't help us a great deal with nonlinear functions, but we can use the linear function to help us understand how we work this out with a nonlinear function. So what I'm going to do is I'm going to work out the total area under the graph there, and the area is 54. So the average value has to be such that I need to have an area, an equivalent area, which is also 54. So and I can see that it's going to be that's going to happen when I have 4.5, unsurprisingly, right? Or that's 54. I need to have the equivalent 54 in the yellow area. I'll cheat and just type in 4.5. Okay, so that shows that the average value is 4.5, quite obviously. So the two grey areas are equal and the two blue areas are equal. So effectively, I'm turning that function into an equivalent rectangle. So I can do exactly the same thing with a non-linear function. So I have this non-linear function. I want the average value between -2 and 6. Now, it's not obvious where that average value is. However, I know that the total area under the function is 28.7. So I need, that's the orange area, so I need an equivalent yellow area also of 28.7. There we go. So it's round about, so the average value is round about 3.58. So I know that the area under the graph is the integral from a to b of f of x. The area of the rectangle is the length of the base, which is b minus a, by how high it is, the average height. So I equate the two, make the average height the subject, and that's how I get the formula for average value. So the formula is very easy to use, but understanding what's going on is more important. All right, so I'm going to find the average value of that function over the interval 0 to pi. So I've got my formula there, which I've seen where the formula comes from. And that's what the graph looks like. And I'm going to work that out. And it's that ugly expression there. But if I want to get a rational approximation, Control Enter, it's just over 2. And let's see how that works. So the orange area, the area under the graph from 0 to pi, is roughly approximately 6.39. So I need an equivalent yellow area that is also 6.39. And it's somewhere around about there. So I can see that, yes, it's round about the 2. So what's happening there is that the grey area above the average value is the same as the 2 yellow areas below the average value. So I've effectively turned that hill-shaped area into an equivalent rectangle, a rectangle of equivalent area. Okay. Now, sometimes on the exam you get conceptual questions where you don't actually need to use the formula. So in this question, which is question 9 on the sheet, you have a linear hybrid function where the minimum is -2 root 2, and the maximum we need to find, given that the average is 3 root 2. So the distance between -2 root 2 and the average 3 root 2 is 5 root 2. So therefore m must be 3 root 2 plus another 5 root 2, which is 8 root 2. So that's a sort of conceptual question which has been asked as a multiple choice question in the past, and it requires no calculation, just understanding what's going on. And in terms of area, what's going on is that we've got the equivalent rectangle, so those areas are equal, and those areas there are equal. All right, so hopefully that illustrates the meaning of average value. And what I've tried to do is to make a connection between the graphical representation and the calculus. So my time has come to an end. So thank you very much for attending today's webinar. And just a reminder that on Wednesday the 17th, there is a webinar on the binomial distribution, one of the probability topics, and the following Wednesday the 24th, the normal distribution. So once again, thank you for joining us and enjoy the rest of your evening.